Imagine a device no larger than a coffee mug resting on a concrete floor. Suddenly, with a sharp crack, it launches 100 feet straight up. When you see a vertical leap of that magnitude, the mind instinctively looks for a massive energy source capable of generating that much force. You expect to find a heavy combustion engine, a dense block of chemical fuel, or a giant pneumatic piston. But none of those exist here. This internal schematic reveals the actual power source, a single, tiny, low-power electric motor. This setup demonstrates that in mechanical engineering, an explosive, disproportionate output can be achieved without an equally massive or exhausting power source. We often carry a parallel misconception about our own careers, the belief that massive professional results require a massive engine of willpower to muscle through tasks in huge, exhausting bursts. Human biology, however, is not designed for sustained high-intensity output. Our motivation tends to fire all at once and deplete rapidly, making raw effort a strategy that often leads directly to burnout. To understand how a weak motor achieves such extreme vertical height, we have to look at how it manages energy inside the lab. The mechanical advantage used here is known as work multiplication. It is a process that separates the force of the input from the final scale of the output. Instead of jumping immediately, the small motor turns a gear, methodically cranking a heavy spring over continuous, low-effort revolutions. This process allows those small inputs to accumulate into a massive reservoir of potential energy, the energy an object stores through its physical state. Work multiplication is the practice of stacking continuous micro-inputs over a long period of time to create a single massive force. But there is a vulnerability in this design. Without a way to hold the tension, the heavy spring overpowers the motor, causing it to violently slip backward and letting the accumulated energy dissipate. The system requires a specific component to prevent that energy loss, the latch. It snaps into the gear teeth, rigidly holding tension after every single rotation. It traps the energy so it can be released in one targeted burst instead of leaking away. This physical engineering principle provides a framework for how we manage our own professional output. A human latch consists of rigid routine systems, like automated workflows or scheduled investments, designed to capture and hold the value of daily effort. Without a systemic latch, the energy from a previous work session constantly resets to zero, making it difficult to convert small daily actions into a compounding result. This is why relying on daily bursts of high motivation is an ineffective strategy. Motivation acts as a leaky latch. Because drive is erratic, the progress made during a productive session often dissipates before a large project is finished, forcing you to use more energy just to get back to where you were. Reliable progress comes instead from hard-coded templates or no-code automations. These structures lock in your forward progress, regardless of your mood or energy levels. Building a rigid system removes the need for high motivation by securing every drop of effort you expend as soon as it happens. This allows for a different approach to massive goals, like writing a book. Rather than a massive weekend push, you apply steady 1% daily effort, relying on your systemic latch to hold the tension of the project. One side represents the exhaustion of relying on biological force. The other shows the compounding ease of turning a mechanical crank that cannot slip backward. High achievers don't necessarily have bigger engines or more raw energy. They succeed by engineering superior latches.